Welcome back to the day 5 discussion, the last day of the Wave Characteristics Relationships Lab. And it's such a good one that it deserved its own video. And here is our story so far. If you don't know where any of this came from, there is a video that accompanies day 5's activity that derives all of this and shows all the graphs. So if that's something you're interested in, and I think it should be, make sure you go watch that. This sheet without the graphs in it, just blank, is available too for you to take notes while you're watching this conversation. And this is the type of thing that we would have been doing in class. So understanding what all these relationships are really important. In this final day, we're just going to look at what happens in day 5 when we put the wavelength on the y-axis and see how that is affected by frequency and period, which you kind of know is sort of the same thing. Here's the data again. We're putting wavelength on the y-axis and seeing what happens when we adjust these. Here's the first one. If you copied the data over and found a graph, this shows how the wavelength varies with frequency. Generally, as frequency increases, the wavelength decreases. And as frequency decreases, the wavelength increases. And when we try to fit this with a model, we get a perfect inverse fit. In other words, let's just take this point right here. When we double the frequency, the wavelength halves. If we were to quadruple the frequency, the wavelength quarters. So this is an inverse relationship. First, we'll just treat it mathematically with the equation, and then we're going to actually look at the wave machine and see if we get an actual feel for how these things are being produced. But if we just translate this into the variables that we actually used, notice y is the wavelength, x is the frequency, and this is the constant that emerges. Now, if this constant is new to you by now, then you really haven't been paying attention. This is the number that continued coming up every time we looked at the speed of these waves. So up here, this is not just any number. This has physical significance, and it is the speed of the waves. So specifically for this set of waves, when the speed was a constant 0.0124 meters per second, that's the number. But generally, this is the equation. And this is nice because it shows lambda, or wavelength, as the dependent variable and frequency as the independent. I like this because of that cause-effect relationship. This is communicating to me that wavelength is a product of velocity and frequency, and we want to make sure we get a feel for that. Now, you might see this expanded into what's often called the wave speed equation, v equals lambda f or v equals f lambda. And this is a little bit more common to see, a good relationship. I think this is a little better for viewing wavelength as something that is produced by a combination of other factors. Let's look at the wave machine to see if we get that. So here's the wave machine producing an oscillating wave, a continuous wave, and over here is this equation that kind of dictates how this wavelength is produced. And what I love about looking at this and looking at this equation is we kind of see both types of motion in here. This v is about propagation, or how fast the wave travels this way, and we can kind of just look at a crest and watch it travel this way. This f is about this oscillation. So we got the two types of motion, propagation, oscillation, and factors in both propagation and oscillation determine the wavelength. So this is what's going on producing this wavelength. So if I put a ruler out here, looks like my wavelength, it's about 1.6, 1.7. Perfect. Okay. Now what were to happen if I then doubled the frequency? what I would predict is this speed is not going to change because I haven't changed anything about the medium. But this oscillation is going to go up and down twice as frequently. So I'm just predicting here, that this crest is only going to get half as far before the next one is produced. In other words, if I double the frequency, the wavelength should be halved, because without a change in speed, the old crest will only be to here by the time the next one goes. So let's see. Yep. And now what we can see, this is a good time to pause it. Here is the original wave at the original frequency, and what we find is that the distance between, the distance of 2 cycles is now the same, because the wave didn't change speed, but the frequency doubled. It's a great picture. It also allows us to think about what would happen if the speed did change without changing the frequency. So if the speed increased without a change in frequency, we would expect this crest to get farther before the next one occurred. Now, that's not something we changed in ours, but really briefly, I'll just show you what happens. If all of a sudden I change this to a higher tension, the wave is going to travel faster. So these crests should get farther by the time the next one's produced, increasing the wavelength. Let's look at that. Yep, very cool. So these were the crests being produced at this distance apart with the slower speed, and without changing the frequency, if we increase the speed, larger crests. And so here's that finding into our table with the correct relationships. And you will see both of these. And here's the wavelength versus period. Now with wavelength versus period, this was a perfectly linear relationship. We would even call it proportional because it has no intercept here. So the intercept is effectively 0. So we're getting, now we're getting an equation where we actually put in the physical variables, wavelength, period, and it looks like it's linear. Not surprising that this number pops up again. It's 0.0125, and wavelength equals v times period. And that is the exact same relationship as this. So this one we put in here, but what you need to kind of recognize is that F equals 1 over T. So, or T equals 1 over F. So if I were to put 1 over F in here, we basically get this relationship. And in similar thinking as we did before, same idea. This is about the oscillation, this is about the propagation. If I were to double the speed at which the wave is traveling without changing the period, each crest would get twice as far before the next one occurred, which would double the wavelength. If I were to also double the time between crests, that would have the same effect. And we could start combining too. We could start saying, what would happen if I doubled the time between crests and made them go twice as fast? So if it was 2 and 2, we would expect a wavelength that is 4 times, right? So it's fine to get the equation here. It's even more important to understand fundamentally what's happening and how wavelength is being produced by a combination of how fast the waves propagate and how quickly the oscillation repeats itself. Thanks. Go ahead and fill in your table with those results.